Okay, all right. So let's discuss all these notes are already uploaded. Processes are processes in which we have a consumable electrode and we have fluxes. So I want to start with flux core arc welding, right? FCAW, and people call it flux core. And let's see. For most practical aspects, this is more or less the same as MIG. We have we might or might not have a shielding gas, but we have a wire that comes in, and we have a contact tip that provides a sliding electrical contact, and the wire advances and melts and falls in the form of droplets, either a few small droplets, a few big droplets, many small ones. But there is a significant difference in this case. And it is that the wire is always cored, and what is inside the core is a flux. And the flux is a bunch of chemical components that melt and create a protective layer to the weld. So, talking about the protection of the weld, we have two types of processes of flux core. One is FCAWS, that is self-shielded flux core, right? This is Lincoln markets this as like an inner shield, right? Some people call it open arc processes, and has in many aspects it's just like MIG, except now you don't need a bottle of shielding gas. You don't need argon anymore. Now, of course, you don't need argon, but somehow you need to protect the weld, and the fluxes do this protection from the atmosphere. And also the fluxes have elements that will react with the oxygen in the atmosphere and will react with the nitrogen in the atmosphere and absorb it and take it to the slag, so it is not inside the weld. Now, you can imagine, you cannot compare the microstructural integrity of MIG or TIG that is done in an inert gas with the microstructural integrity of something that was exposed to oxygen and nitrogen, and you just somehow scavenged it how well you could. Now, there is other flux core processes that are called dual shielded, right? FCAWG. And in this case, it's very much like MIG, because now you do have a shielding gas, right? Often it's pure CO2. Sometimes it's blends of CO2 with other things like argon. The more argon you have, the better. Also more expensive. I added here a gas that is being marketed recently that is CF4, and that is carbon. Well, it's a molecule of carbon and fluorine, and the fluorine scavenges hydrogen. Hydrogen is often a problem in welding, so the fluorine takes hydrogen away. So much like MIG, the wire is automatically fed. The polarity runs on constant voltage, much like MIG, typically electrode positive when we have gas shielded, or electrode negative when it is self-shielded. Those are typical polarities. For flux core, we seldom use waveforms or alternate current. Typically, it's just straight DC. Now, what is awesome about flux core? Right? It works in the field because, especially the self-shielded one, I don't have an inert shielding gas that is blown away by the wind. So it's very robust. For those of you who are familiar with stick welding, this competes with stick welding. However, it has much higher productivity than stick welding. Also has an advantage over MIG, because you might wonder, why would I use shielding gas if I also have the slag protection? I mean, shouldn't I have one or the other? Well, one of the cool things is that the slag, in addition of protecting from the atmosphere, the slag also holds the molten metal in place. So with flux core, you can make welds out of position. When it gets shielded, you can make them out of position because the fluxes help to keep the metal in place. In MIG, you don't have these fluxes. So doing out of position, you're relying only on surface tension, and you don't have the help of a slag layer that is holding your weld in place. Now, of course, flux core is not a process to do detailed welds, right? This is not TIG. You don't use flux core to make welding of rockets or to make a welding of race cars, right? However, it has an advantage. If you are welding in the construction industry and you need to weld a girder that is on floor 25, you'll be a lot happier if you take a torch without a bottle, and not that if you have to be hauling a bottle with you, right? So it's very practical, flux core arc welding. Because flux core arc welding is tubular and has these powders inside, the powders can absorb moisture. And so flux core arc welding is not as low high hydrogen as MIG or TIG. So now we're getting into the range of hydrogen content that compares to stick welding, which means in some cases we need to deal with preheats. Flux core wire needs lots of care and love when we're using it for low hydrogen application. I was told once something, I'm not too sure how true it is, but that is that once you open up a roll of flux core, you use it. And at the end of the day, whatever you don't use, you trash, right? And I don't know. I grew up like picking up stubs from stick welding to do my welds. It's hard for me to believe people tossing an unfinished spool. But that's one of the problems with flux core. Okay, so flux core, you have the wires much like metal core, you produce them the same way. One thing, if you remember, I mentioned that moisture can be a problem. So moisture would come in through these little spaces in the seal, right? In the seam, you have a seam and moisture can come in. Now, the Japanese, and I'm sure they're not alone, they sell these wires that are seamless. Would you believe that they go through all this process, making a flux core wire, and then they do a longitudinal laser weld of the wire? So what you're melting is already a highly manufactured product which involves a longitudinal laser weld, right? Now, if it is all welded, then it's airtight and you don't have these problems of moisture. And so when you're welding high hydrogen applications, these seamless wires can come in handy. So let's, I have one of these videos for the Society of Manufacturing Engineers about flux core. I believe I'm sharing with sound. If it is not sharing with sound, please send me a note through the chat box.
Flux core arc welding uses a filler metal made up of a tubular electrode with a flux core and with or without additional gas shielding to join carbon steels, low alloy steels, stainless steels, and cast iron. The core may contain minerals, ferroalloys, and ingredients that provide shielding gases, deoxidizers, and slag-forming materials. These ingredients promote arc stability, enhance weld metal properties, and improve weld bead contour.
All right. They didn't say, oops, they didn't say a whole lot, but I want to show you in this video here a comparison using videos we took in our lab between the metal transfer of flux core, right? You just saw MIG, right? And you saw what the spray and globular looks with MIG. And now I want to show you what the metal transfer looks for flux core. On the left, we have flux core that is self-shielded, no gas, electrode negative. On the right, we have flux core that is dual shielded with high argon and an electrode positive. So something to focus your attention on this is on the right, you see that the arc attachment is more or less constant. That is typical of electrode positive. On the left, you see, and you have to have it trained that, but you see that the arc like dances right and left. And the arc dances right and left because it's electrode negative. And electrode negative tends to have a more erratic arc, because we'll discuss this when we discuss arc physics. The other thing you get to see is that flux core has very different metal transfer than MIG. MIG were these perfectly defined droplets, but in flux core you see all these spatter, right? They are not as beautiful droplets as we have in MIG. Now, between these two videos, left and right, if you pay attention, you're gonna see that there is quite a bit more spatter, these droplets flying that I'm tracing here with my pointer, right? There is more spatter in the self-shielded than in the dual shielded. And of course, because in the dual shielded, we have an inert gas shield, but in the left one, we have all kind of sparkles because we're reacting with oxygen and reacting with nitrogen and trying to scavenge it and take it out into the slag. Because we have all these alloying additions like aluminum to react with the oxygen, right? Now, most of those go to the slag, but not all of them. So a self-shielded flux core well deposit tends to have quite a few non-metallic inclusions, even if they're at the microscopic level. And the end result is that the toughness of flux core arc welding when it's self-shielded is pretty low. That's what we use for civil construction. But guess what? Toughness is seldom required to qualify a procedure for civil construction. Those of you who have been exposed to procedures for pressure vessels, you live and die by toughness. You have to pass Sharpie, and you care a lot about toughness. Civil construction, completely different world. People seldom, if ever, ask about toughness. So briefly, and if all goes right, I want to have a whole class on welding fluxes. But fluxes are incredible. Fluxes are mixtures of minerals. And although people will describe fluxes based on their chemical formulation, you could not possibly afford an electrode that is made based from like chemically pure components. So when people talk about, I don't know, calcium silicate, or talk about, or potassium silicate, right? Though that means they went to a mine somewhere in the world and they dug out a mineral that has lots of this calcium silicate, and then they grind it, but it's never perfectly pure. So they have to get this formulation by balancing all that they can get, and you should get always the same result. Flux formulation and quality control is extremely difficult and complicated. And the fluxes have many functions. I mentioned one is to protect the molten metal from reactions with the atmosphere. But also, the plasma, you don't have argon anymore. And much of the gas in the plasma comes from the evaporation of the flux components. So the flux has to give you an adequate plasma. And we're going to see when we study the physics of the plasma, how, for example, 6010 can only be used, electrode 6010 in stick welding can only be used with DC, and 6011 can be used with AC. It's all because these components of the fluxes have properties of stabilizing or not the plasma arc. And in addition of giving you good plasma, and in addition of giving you good shielding, when the slag starts to go solid, it's meant to hold the molten metal in place, right? That's why we can do very good out of position welding with flux core, right? And also the fluxes have chemical elements that are meant to react with oxygen and nitrogen. I mentioned, for example, aluminum. Sulfur, for example, has manganese, which also reacts with oxygen. React with the phosphorus. You want to have all these chemical elements that have chemical reactions. So to some extent, each weld is a very sophisticated operation of steel making, right? Welding is incredible. When you buy an electrode and you weld, you don't realize that what is happening is way more complex than steel making. Some electrodes, some fluxes add alloying elements, right? You might as well put some chromium in there to start tweaking your alloy. And in addition, these reactions that happen, they have to make whenever they clean the sulfur or the oxygen or the nitrogen, they have to float and not to sink, because if these inclusions sink, we would have all these non-metallic inclusions at the fusion line, right? All these things need to happen. And in addition, after everything is said and done, I have my slag on top of the weld, which needs to be removed. I mentioned in one of the previous classes, when you see the hammer, the welder hammering at the weld, what they are doing typically is like chipping off, removing the slag. And if the slag doesn't come out easily, it's a nightmare. To give you an idea, what my advisor, where I did my PhD, one of my predecessors did a doctoral thesis on slag removal, a PhD thesis from MIT on slag removal. Isn't this crazy, right? It was for the Navy, because if you cannot remove the slag, you have problems. We had a project with a company making overlays using a process that involves slag. And to remove the slags, they went and got a jackhammer. And the slag were so hard and so resistant to abrasion that the jackhammer wore out, and they still couldn't remove the slag. So look at that, something that seems like a small detail. True or false? Anybody wants to venture a guess? Flux core is often run in a MIG machine. Thoughts on the chat box? Oh gosh. Okay. True, and thank you very much. But what I see is most of those who replied are people who have already welded. So yeah, same thing. We have 4 more minutes, and I want to start discussing submerged arc welding. And the first thing I'm going to tell you is that if you are like me, I need to dispel a misconception. Submerged arc welding has nothing to do with welding underwater. they call it submerged arc welding because it's submerged under fluxes. I think it's horribly misleading name, but it's the name it has, SAW, submerged arc welding, and it's not done underwater. So let me introduce this to you in these last few minutes we have. I group these processes around similarities. And we started talking about TIG because it has an arc. And then I said MIG because the arc now melts the electrode. And then we started to talk about fluxes. And subarc welding, to some extent, is very similar to MIG. You have a wire that melts in the form of droplets, and you have an arc, and then you have a base plate, very much like MIG. Now, the difference is that instead of like having a blanket of inert gases protecting your metal from the atmosphere, what you have is a blanket of flux powders. Now, this difference that to some extent sounds like a subtlety in the mechanism makes the two processes look very, very different. And they have very, very different applications too. So in this schematic, what we have here is the electrode melting, we have the droplets, we have the plate. And this thing here, this dash is the bed of flux. And the arc is under this bed of flux. And right near the arc, the flux is molten, right? And it's becoming slag. And the slag reacts quite a bit with the molten metal, just like what we discussed in flux core. Typically in submerged arc welding, the wire is solid, but the wire could be also metal core or other things. It's much like what we have discussed so far. But in this case, you never use a gas. And something interesting, because the arc is happening under this layer of powders, you don't see the arc. So it's a very different process than MIG. And because you don't see the arc, actually, when this process was invented around 100 years ago, people were wondering if there is an arc at all, or what's going on in there. And about 5 years ago, we had a project involving subarc, and we hired, no, we didn't hire, but our sponsors hired a consultant, a highly paid consultant, who had the theory that the electrode was rubbing against the bottom of the weld pool. That's the 100-year-old like doubt they had. But I'm gonna tell you right now that yes, there is an arc, and no, the electrode does not rub the bottom of the pool. So in these last few seconds, let's talk about the protection of the melt is with a flux. And the flux has a property called basicity, which we'll discuss later, but essentially controls the amount of oxygen in the weld, essentially the amount of oxide inclusions. And something else called neutrality that controls manganese and silicon. Because manganese and silicon are good to react with oxides on the plate, you might want to have more or less manganese and silicon depending on how rusty your plate is. And I think this is a good point to stop here in subarc welding, and we're gonna pick up subarc welding on Thursday. We're going to stop our lecture now, and at 3:30, in 10 minutes, we have the seminar in which Alejandro prepared video demos of TIG welding and PTA welding, which I think are pretty good. And for you, it's gonna be our premiere. So let's stop here.